All right, thank you, Arjen. Thank you for the opportunity to begin those ETSF seminar. I'm very glad to start off. So yes, as you said, I'll be talking about remote electron-phonon interactions and screening in van der Waals heterostructure. So I tried to depict such an interaction here. So you could have a phonon in one 2D material, one layer, and an electron in another. And there could be some interactions in between the two. So I work indeed at Liege University with Mathieu Verstraete, that I think a lot of people know here. And all this work has been done in very close collaboration with Marco Ghibertini at University of Modena. Okay, so van der Waals heterostructures is this game that a lot of people are playing these days. The game is to stack 2D materials that are bound together with van der Waals forces, and each material should bring some functionality or be a way to enhance and design the properties of the whole. And it's probably not exhaustive, but here I've tried to put three big categories of the type of things you can do by adding 2D layers around a 2D material. So there's protect, control, and engineer. Protect would be when you want to maintain the intrinsic properties of a target layer. So you want to kind of shield it from external perturbations. And for example, you can kind of clean up the optical responses of TMDs by capping them with boron nitride. Control is when you want to give yourself some kind of knob with which to tune or switch the properties of some material. A typical example is like when you stack up some dielectric and metallic layer on top of a semiconductor, and this will allow you, for example, to tune the carrier density in the semiconductor by field effect. And finally, the category that I'm most interested in today is engineer. And here it's really to exploit the interactions between the layers to trigger some new properties and to go look at some new physics. And I'll give an example of such an application at the end. But first, whatever the category to study these systems in general, we would like to be able to simulate them with ab initio simulations to kind of guide all this design. And it turns out that it's not that easy. It's quite challenging, at least for all methods that rely on periodic boundary conditions and going to reciprocal space. And so that's because we exploit the periodicity of the crystals and basically bring ourselves back to calculations whose cost is proportional to the number of atoms in the unit cell. So here, for example, in gallium selenide 2D layer here, the unit cell has 4 atoms. But if you want to do some van der Waals heterostructures and stack different layers with different periodicities, you're going to have to come back to something periodic, and you're going to have to find a superstructure that kind of accommodates both periodicities. And you'll have to do this by rotating and straining one layer with respect to the other. And here in a very simple case of gallium selenide with boron nitride on top, even allowing a relatively generous 3% strain in the boron nitride, the best you can do is this supercell here with already 34 atoms. And this is not this is a relatively easy case. Like in general, it's very hard to find small supercells. And so, as I maybe have mentioned, the cost of the calculations increases the cube of the number of atoms in the unit cell. And when you look at phonons, electron-phonon interactions, you also have the number of phonon modes that grows as 3 times the number of atoms. And your calculations start to be very, very, very expensive. So That's an issue, and one possible solution to kind of circumvent this this issue is to go as far as possible ab initio, but stay at the level of the layers and treat the interlayer interactions with some semi-analytical model. And of course, this kind of model is going to be necessarily focused on some physics, some mechanism, and there's going to be some other mechanism that we're going to have to neglect. But as we can see, as we'll see today, we can do already a lot of interesting physics with this kind of strategy. And in particular, we can study electric field-driven electron-phonon interactions, such as the Frohlich interaction between electrons and polar-optical phonons. So this is just a little reminder of what the Frohlich interaction is, with like a focus on the difference between 3D and 2D, in case some of you are mostly familiar with the 3D version. So in most semiconductors, you'll have different atoms carrying different effective charge. And when you move those atoms with respect to each other, you create dipoles. Now, if you consider a displacement pattern such as the one of polar-optical phonons, you create some polarization density from those dipoles, some periodic polarization density. And this will in turn generate an electric field. The electric field is different in 3D and 2D, as you can see from this green Coulomb kernel here. And the underlying reason is twofold. First, because the source of the field is in different dimensionality. It's either a volume of dipole or a plane of dipoles. And also because the material screens those fields differently. In any case, those electric fields, when you apply them to electrons, you get a kind of electron-phonon interactions that's called the Fröhlich interaction. And it's different in 3D and 2D. Here, for example, in MOS2, if you look at the bulk, the interaction diverges as 1 over the momentum, whereas in one single layer, it goes to a finite value here at gamma. So it might look a bit minimal as a difference, but actually a lot of properties depend on the integral of those couplings on all momenta. And so when you integrate something that diverges or something that stays finite, you get quite a significant difference. So today we'll be mostly interested in the 2D version, of course, but what I'd like to stress here is that this kind of interaction is mediated by electric fields, which means two things. It's going to be sensitive to screening, and it's going to be able to act from a distance. And this is very crucial when you start to consider van der Waals heterostructures, because even though the dipoles are so confined to a plane, the potentials and the electric field generated by those dipoles extend in the out-of-plane direction. And we do know, we have some analytical expressions for the potential generated, so related to the electric field. So this is the bare one before any screening. This prefactor here is just dependent on Born effective charges. And here you can see the form of the out-of-plane variation of this field. Well, potential. And basically it extends in the out-of-plane direction on a length scale that is proportional to the wavelength of the perturbation, which is this polar-optical phonon in this case, and so inversely proportional to the momentum. In particular, at long wavelength, the fields extend very far in the out-of-plane direction. Now, if you consider that you put some kind of other materials around, those are going to feel those potential, and they're going to respond dielectrically to this perturbation. And you're going to end up with a screen potential that is different, not only in this layer, but it's also everywhere. So it's going to be felt by all the electrons around. So there are two kinds of interlayer effects here. Even if you consider the interactions between electrons and phonon within the same layer, this interaction is going to be changed by the screening around that comes from materials around. And you have this remote Frohlich interaction between polar-optical phonons in one layer and electrons in the other, and vice versa. Okay, so this is the kind of things we'd like to study and to model semi-analytically to avoid having to simulate all those from ab initio. We built our van der Waals electrostatics model. So it's an electrostatics model because we're going to assume to be in the adiabatic approximation. So we assume that the atoms move much slower than the electrons, and we can work with omega goes to 0, and so a static perturbation. So the form of a general electrostatic problem is you have a perturbation that generates a carrier density response, and this induces a potential, and then the total effective potential felt by the electrons around is the screen potential, which is the sum of the perturbation and the induced potential. The induced potential tends to counteract the perturbation, so it's like opposite, and the screen potential ends up smaller than the perturbation. Okay, and you have this kind of situation here in each of the n layers of our system. And we consider perturbations that can be periodic, that are periodic in the plane of the materials. So we transform them and use the momentum, the in-plane momentum Q as a variable. And they can have any form in the out-of-plane direction. So we keep the Z variable here. So all of those problems as a function of those two variables. So now, to solve this, two major steps. First, we need to extract single layer response functions chi, so that gives the charge density response as a function of the potential perturbation for each layer from density functional perturbation theory. And then we solve our entire system by doing some approximation that comes down to neglecting the overlap of wave functions or of densities between layers. Okay, so the first step, to extract the responses, we assume that the response functions have this form, so the sum of a monopole and a dipole contribution. They essentially capture the zero and first order derivatives of some, with respect to the out-of-plane direction of some potential perturbation. And to go and measure them from the FPT, we perturb our system with either a potential that is constant in the out-of-plane direction or linear. And then, so those, here you have the amplitude of the response, and then the profile, some kind of projector on the monopole or dipole response. As you can see, the profile in the out-of-plane direction here are non-trivial. They depend on the material. And for example, here in gallium selenide, there are kind of two sublayers, and that's why you see those two peaks. And we want to keep all this complexity in our model, because the out-of-plane variation of the fields and the density is important in our model. So we keep all this, and this is all encoded into those profile functions for the monopole and dipole here. And then the amplitude and the response as a function of the momentum of the perturbation is mainly captured by those parameters here and here. Okay, and we do all this with quantum espresso with a two-dimensional cutoff of the Coulomb interaction to avoid any interactions between periodic images. Okay, so this basically gives us the response of any layer to any potential perturbation, static one. And now we need to put them together into the van der Waals heterostructure and solve the system. So we rewrite this perturbation, gives charge density, gives induced potential, but for each layer of our system. And then we make the assumption that each layer responds actually to a perturbation that is the total external potential plus the sum of the potentials induced by all other layers. And then we compute the response to this perturbation. And as you can see, the induced potential of a certain layer is going to enter the perturbation of all the other layers. And so you have some kind of self-consistent system here that can be solved with linear algebra. Okay, so once we solve it, we have all the induced potential. We can compute the screen potential as the sum of the external one and the sum of all the induced potentials. So this is, in principle, like all of this is a function of momentum and out of plane z. But so we use effectively those projector function I just showed to get rid of the z variable, and we're still left with the momentum dependency, and effectively we end up with a system of equations to solve for each momentum in which we are interested in, and that's what we do. Okay, so this might be a bit obscure. Yeah.
Sorry, could I just inquire? You call it Van der Waals electrostatics at this stage, but yeah. As far as I can see, the Van der Waals hasn't come in yet, or at least the Van der Waals is used to calculate the original structure, but the perturbation you're now considering is nothing to do with Van der Waals.
Nothing to do with Van der Waals interactions. Yeah, I'm using Van der Waals as like a stack of 2D materials. Rather.
Yeah, sure.
Yeah, yeah. The name might be misleading in that sense. Sorry. Okay, so yeah, and here this is just a little example with just 2 layers to kind of see what it looks like in a simplified case. So layer 1 would be perturbed by just the external potential and the potential from layer 2. And this induce carrier density and induced potential, and this induced potential disturbs the layer 2 and so on and so forth. Okay, so we solve this, and then we have so a little model to simulate the response of our stack of 2D materials as a function of any potential perturbation. And now we can talk about this, what I mentioned in the beginning, which is to try to engineer some properties in our Van der Waals heterostructures, and we're going to talk about like remote free carrier screening. But before, I need to give a little bit of context and talk about a little bit about my previous project, which was essentially to find high conductivity 2D semiconductors within a database of many potential 2D materials. And so I found a few with very, very high conductivities and mobilities. They're plotted here. And I compute their transport properties, so conductivity or mobility, thanks to a homemade transport code that solved the Boltzmann transport equation with some electron-phonon coupling matrix elements computed from density functional perturbation theory. And so this is the results. Conductivity is a function of the gap. And I've noticed that for many of those materials, and at least all the ones that are doped by electrons here, yeah, I forgot to mention, I was looking at the conductivity of those semiconductors when they are highly doped with the kind of doping we see here at 10 to 13 electrons or holes per centimeter square. So I've noticed that a lot of those materials and all of the electron doped ones are limited by Fröhlich interaction, and which means that even though their conductivity is pretty high here, it's not infinite because of the scattering on polar-optical phonons through the Fröhlich interaction. And what this also means here is that even though their mobility is pretty high here at high doping, it tends to degrade when you go to lower doping. And that's a problem because you might want to have a material that transports electrons pretty fast on a wide range of carrier densities. And so the first step is to understand a little bit more what happens. Of course, so this is because of the Fröhlich interaction. And so to study this a little bit more in detail, we can look at gallium selenide. I've mentioned it earlier. It's a prototypical kind of semiconductors limited by Fröhlich interaction. As you can see, so its mobility at high doping, 10 to 13, is this. And if you do the same calculation in the low doping neutral limit, you get a much smaller number that you see here. So what's happening here is the blue curve is the mobility as a function of temperature. So it's effectively this number, but as a function of temperature. And in orange is what you get if you do the same calculation, but you just turn off the Fröhlich interaction. So you turn off the interactions with polar-optical phonons, and you can see the mobility shoots up by an order of magnitude. In green is what you get if you do the same calculation, but you swap the electron-phonon coupling matrix elements from the neutral material to the highly doped one. And again, the mobility increases a lot. So what this all tells you is that Frohlich is the culprit. This is what limits the mobility. And whatever happens when you dope the material, it kills the Frohlich interaction. Okay, so whatever happens is not a secret. It's free carrier screening. You can see it pretty clearly if you plot the coupling here in neutral or doped gallium selenide, the coupling with polar-optical phonons as a function of momentum. And as you can see here in the doped case, the coupling is strongly suppressed in the long wavelength limit. And that's due to some screening from the free carriers you add in the conduction band when you dope the material. Okay, so this is the free carrier screening that you need to get this kind of mobilities. But if you want to have the same behavior at low doping, well, you're kind of stuck because if you decrease the doping, you're going to deplete those free carriers here, and you're going to lose the screening that goes with it. So you're a bit stuck, unless, of course, you can use Van der Waals heterostructures and try to maybe bring this free carrier screening from an external source. This is what we're trying to do here, essentially. So we have gallium selenide, and we stack it up with some highly doped graphene, which will have plenty of free carriers to screen. And we have to separate them with boron nitride in between to isolate them electrically. Okay, then the general idea is that there's going to be some polar-optical phonons here that are going to generate some Frohlich potential, which will induce the free carrier density response in graphene, which will in turn screen the Frohlich potential in gallium selenide. And hopefully we can get rid of this Frohlich interaction and increase the mobility. Okay, so we plug this system in our flow model and solve it to see a little bit what happens. So here we plot some potential as a function of the out-of-plane variable. And for two momenta that are in a range that is relevant for transport, because this is usually what I look at. So those momenta are at both ends of this range, so rather small and rather large. And to understand all those plots here, one needs to remember that a planar charge density will generate a potential that decreases in the out-of-plane direction as exponential minus qz, starting, of course, from the source of the charge density z0 here. And that's essentially all we see in those plots. So here the dashed line is the bare Frohlich perturbation generated by gallium selenide here that is placed at -5 angstroms here. And as you can see, it decreases in the out-of-plane direction rather slowly here because we have a momentum that is rather small. So this exponential decay here is rather slow. And so by the time you reach graphene in green here, the bare perturbation is still rather high. And since graphene has plenty of free carriers, it will act as a metal and it will induce a potential here. The negative potentials are all induced potentials. It will induce potential that is almost as big as the perturbation, but opposite sign. And now if you follow this potential back to gallium selenide here, it will decrease a little bit too. And by the time it gets there, it's not as big as it was on graphene, but still there, and it will help to counteract the bare-Fröhlich perturbation. And in the end, so you have contributions from the other materials as well. And in the end, you get a total screen potential in black here that is quite smaller than the bare perturbation here. So this was a relatively large wavelength, but in the very long wavelength limit, so small momentum, this decay here is very, very slow with respect to the thickness of the layer. So this is going to be really flat, and graphene is going to feel the full perturbation. So it's going to give a full response, and it's going to compensate it completely. And the induced potential is also going to be flat, and the bare Fröhlich potential is also be completely screened on the gallium selenide layer. So perfect screening in the long wavelength limit. Now, at larger momenta here, what happens is that the potential decays a bit faster in the out-of-plane direction. By the time it reaches graphene, it's much smaller, it's almost zero. And so the response induced by graphene is also very small. And what happens effectively is that gallium selenide takes care of most of the screening by itself. So we recover a situation that's similar to isolated single layer gallium selenide. Okay, and all this you can see in this plot of the Fröhlich interaction as a function of momentum that we get exactly from those simulations. So in the neutral single layer isolated gallium selenide case, you get this, and this is still neutral gallium selenide, but with boron nitride and graphene on top. In the long wavelength limit, they behave similarly. That's what I said here. And in the long momentum limit, sorry, in the long wavelength limit here, the screening is perfect and the coupling goes to zero. And this is what I was saying there. Okay, so this is the main functionality of like adding this graphene layer, doped graphene layer around. Now, to be a bit more realistic, we also need to take into account that we want to study the mobility as a function of doping. So we can add some doping into the gallium selenide, and we do this by adding, like injecting some free carrier screening in the density response of gallium selenide. This is computed numerically with the FT bands. And essentially here, you add carriers to gallium selenide, you're going to add some free carrier screening to what is already there from the graphene. And so the situation only gets better. So that's not really a problem. The main functionality, as I said, is already done. And then to also be kind of exhaustive, we have to take into account that we added BN in our system, and BN does have some polar-optical phonons of like itself, and those polar-optical phonons can couple remotely to the electrons in gallium selenide. We can simulate this, and this is what we do here. So you can see the coupling is the same order of magnitude as the one in gallium selenide, but the difference here is that the phonons in the optical phonons in boron nitride have much higher energy, and so at room temperature, effectively, they're not populated and they don't participate to transport so much. So even though the coupling is rather large, in the transport, they don't matter so much. Okay, so this is the final result. This is the mobility as a function of doping in our gallium selenide boron nitride graphene heterostructure. The two dots are reminders of what you get in isolated gallium selenide, either highly doped or neutral limit. And we said that the difference here is due to the loss of free carrier screening that you get when you decrease the doping. In our van der Waals heterostructure, thanks to the graphene, we managed to keep a rather high mobility, because as we lose the intrinsic free carrier screening from gallium selenide, this is compensated by the free carrier screening from graphene that acts remotely, and we manage to stay at relatively high mobilities around 500-600 centimeters square per volt second. So this is like a simple way to keep the mobility high, and this is relatively general. It's also applicable to all those other materials I mentioned quickly a few slides ago, and in general to any material that is dominated by screenable electron-phonon interactions. Okay, so those are just some conclusions. This paper, you can find all the details of what I've showed today. It's a QR code to this paper, and yeah, various things to thank, and thank you for listening.
Thank you very much, Thibault. Are there any perfect on time, by the way, very good. Are there any questions? Just unmute yourself and ask the question. Somebody's typing the question. Claudio.
I have a question. Thibault, what about the other phonons that are not Frohlich? Do you think they are important or not?
So we are slowly adding things. So all phonons that generate some electric fields of some kind are going to be important. So you also have the piezoelectric phonons. They will, I don't know, we don't know exactly how far they extend in the out of plane direction. We don't know how strongly they will couple and how this changes with screening, but in principle, they're there. Then maybe you have some out of plane phonons that will generate some fields. We're exploring this, but in general, yes, anything that will generate an electric field can be remote. Other things, in principle, they're more local. So gauge field kind of pseudo-magnetic things like happens in graphene. In principle, they stay in the graphene. But yeah,
I had a question. I was wondering if anyone knows whether this is stuff that people did in 3D semiconductors since the 60s, like maybe a Russian person or something. Is this so well known in other communities maybe, or in outside of 3D materials, if 2D materials?
It's not in Landau Lifshitz, Mathieu.
So then it doesn't exist.
How could there be an analog in 3D, because you don't have anywhere to put the screening layer?
Yeah, I'm thinking of thicker heterostructures they make out of gallium arsenide and this kind of thing. And my impression is maybe some of their devices were working much better since the 70s because of this effect, without even knowing that it was implicitly screening some of the scattering. They were introducing, doped layers within semiconductor heterostructure, and I don't know. I don't know if this is.
I think screening from the gates. Yeah.
Oh, sorry.
Yeah, screening from the gates is something that in the transistor community has been taken into account. But there's a proximity here that is allowed by 2D materials that really enhance the effect. Here I've not clearly shown it, but if you put more layers of BN in between the gallium cyanide and the graphene, if you increase the distance, this effect is gonna decrease as well. And so if you imagine like a dielectric that is 10 hundreds of layers, then you kind of lose this thing. So there's a really specialty to 2D layers. So Claudio, sorry I interrupted you.
No. It was just a comment. I know it's something different, but there was all the work about Simone Fradini and other people that you study the effect of phonons of substrate on monolayers, but it's slightly different.
It's remote. Those remote electron-phonon interactions. They're part of the stuff here. Yeah.
Thibault, do you have any way of benchmarking your models by doing some full ab initio calculations on simpler systems? I guess that the systems that you now, they're too complicated to do. I mean, they're too big to do.
Yeah, so we've done some stuff on bilayer BN. Sorry, there's not a lot of legends here, but yeah, this is for BN. This is essentially the potential response. We can focus on those. So this is monolayer BN, and so the model for monolayer reproduces things pretty well. This is bilayer BN, so you can see the two bumps here. And actually, this is bilayer BN at a rather like rather close to where the two layers are rather close to each other. Or is it this one? Wait, no, here. Okay, this one they're closer. Bilayer BN with the two layers rather close to each other. And oops, that's not what I wanted to do. And here you can see if you look very carefully that the agreement is not perfect.
We don't see your screen anymore.
Ah. Oops. Sorry. And I have to go back to Zoom.
Anyway, the dots were the ab initio calculations, and then it was the...
Yes, dots are ab initio calculation, and the line is the model, exactly. So monolayer is perfect. Bilayer with a relatively small distance between the bilayers. You see some small differences, especially in between the bilayers, and that's the effect of this approximation, that we neglect the overlap of the densities between the layers. So here we're missing something, and just to confirm that it's this approximation, we also did the calculation by increasing the interlayer distance, and here we go back with like almost perfect agreement between the two. So it's really this interlayer approximation here. And so yeah, that's the little bit of testing we've done. And as we're probably going to test a bit more complicated systems with some like reasonable supercells. But yeah, something like with 3 different layers, it gets very complicated to simulate directly.
Okay, thanks. Are there any other questions? Maybe you can ask just another one. I was just wondering, the free electron model, the free carrier model, does it matter a lot if you choose a simpler model? Does it like Thomas Fermi screening or Lindhardt?
So in this case that there's a lot of equations, but yeah, this is the simple model we use here. In this case that I've shown today is gallium selenide. It has a nice and isotropic, clean conduction band. So no, I don't have it. I don't have on the slides, but yeah, it's like a nice isotropic band structure. And so in that case, yes, if you take the effective mass and do some classic Thomas Fermi, I don't expect to see big differences. But I've seen some more serious differences in more complex material with multi-valleys or multiple valleys, or valleys that are weirdly shaped, not isotropic, and all this. So we had the possibility to compute this numerically because I have like the band structures on very fine grids, and so we just included it. It didn't cost much to do this fully.
Okay, thanks. Okay, last chance for some questions. I don't see any other questions, so let's thank Thibault again for this nice seminar. I remind you that the next seminar is in 1 month, the 26th of March, same time. And also I remind you that if you want to propose somebody for one of these ETSF seminars, just write me an email. And also, it's probably good to remind you to tell the members of your groups to register as ETSF members, since for the moment we send out the, let's say, the Zoom invitations only to the members. I don't know if Mathieu wants to add something.
It's great to see you all. I miss you all very much.